Welcome to the Deep Dive, where we take complex ideas, cut through the noise, and give you the distilled insight you need to truly understand the world a little better.
And today we are focusing on something that is, well, deceptively simple. The overlapping circles known universally as the Venn diagram.
Right.
It's a visual tool that's so ingrained in how we think now that it feels almost natural, like it's always been there. You see it in textbooks, in business presentations, and of course all over the internet in memes.
Exactly. It's the universal shorthand for intersection and exclusion. You use it in, third grade to understand what a set is, and then you're still using it in graduate school to analyze data clusters. But that familiar simplicity, those clean overlapping boundaries, they conceal what is actually a remarkably convoluted and, I was surprised to find, often contentious genealogy.
And if you ask most people, who invented this iconic shape, they'll give you the right name. They'll say the British logician, John Venn, sometime around 1880.
And while that answer points to the man who really standardized the form that bears his name, it is, as we so often find in these deep dives, historically incomplete.
Very incomplete.
Yep.
Venn wasn't operating in a vacuum at all. He was, in fact, refining and, I'd say, rigorously systematizing a visual language that had been established and popularized over a century before.
By one of the greatest minds in history, the Swiss mathematician Leonhard Euler.
That's right. So our mission today is kind of twofold. First, we have to trace the full lineage of this diagram, and that means starting centuries, literally centuries, before Euler.
Okay.
And second, and this is really the crucial part, we need to analyze the specific technical and philosophical innovations that Venn introduced. These were innovations that were necessary to align this diagram method with a whole new field of algebraic logic.
And that forced a complete departure from the intuitive model that Euler had set up. And this is where the conversation moves beyond just drawing circles and gets into philosophy. This isn't just a disagreement over how to draw things. It's a battleground between two totally distinct ways of understanding what existence means within logic. We are really exploring the conflict between, on one hand, the ancient Aristotelian logic of actual things logic that requires subjects to exist in the real world to even be discussed.
And on the other hand, the newer Boolean logic of hypothetical classes. These are classes that might very well be empty.
It's the journey from a visual aid that was designed to describe what is, to a universal standardized template that's designed to map the entire universe of what could be.
That's the leap.
Okay, let's unpack this historical journey, and let's start long before the age of Enlightenment mathematicians. The fundamental human urge to visualize logic, to map abstract thought, spatially or mechanically, it's incredibly deep.
It is. And to find the earliest credible ancestor of these visual systems, we have to leap all the way back to the 13th century.
Yep.
We're starting with a figure named Ramon Lull. And he's a man who truly transcends any easy categorization. He was a Majorcan philosopher, a mystic, a theologian, living from roughly 1232 to 1315.
And his work represents the very first significant attempt to mechanize the process of reasoning itself.
That's it. His central and most ambitious work was called the Ars Magna, or the Ars Generalis Ultima. He finalized it around 1305.
What's so astonishing about Lull isn't just the complexity of his system, but the theological ambition that was driving it.
Absolutely. Lull was driven by a missionary zeal. He studied Arabic. He sought to convert non-Christians, particularly Muslims and Jews, not through, rhetorical argument.
Oh, and not by persuasion.
No, but through what he genuinely believed was irrefutable mechanical, logical demonstration. He thought he could build a device that, when you operated it properly, would just prove the divine truths of Christianity beyond any doubt.
And this belief manifested as the famous Lullian logic machine, these devices that were based on paper constructs called volvels.
That's right. Imagine a series of concentric circular discs, made of parchment or card, mounted on a central pin so they could all rotate independently.
Okay.
And on the rim of each wheel, he inscribed symbols, often just represented by letters. And these symbols stood for core concepts.
What kind of concepts are we talking about here?
So in the earliest versions of the Ars Magna, the innermost wheel might carry the letters representing the core divine attributes: goodness, greatness, eternity, power, wisdom, and so on.
And the outer wheels.
The wheels outside of that would carry more general logical categories like subject, predicate, difference, identity. things like that.
So by manually rotating these disks, you could line one attribute up with another, say lining up goodness with eternity, and you could generate every possible combination or relationship between the concepts you wrote down.
It was a mechanical way to generate logical pairs or triplets or even more complex propositions. Lull saw this process of combination as revealing the underlying necessary truths of the universe.
This physical, externalized, logical schema must have been radical for its time.
Oh, profoundly influential, especially on later generations.
Yeah.
Gottfried Wilhelm Leibniz, in particular, studied Lull and was just captivated by this idea that reasoning could be algorithmic.
But this leads us to the critical distinction. This is what separates Lull from the tradition that leads to Euler and Venn. Lull's diagrams were fundamentally combinatorial.
Precisely. Lull was concerned with generating associations. Does goodness relate to greatness? He was showing a dynamic pairing of concepts. He was not interested in representing the spatial extension of a class.
So in other words, he wasn't trying to draw a circle for all good things and another circle for all the great things and then see how much space they shared.
Not at all. The idea of a static topographical representation of logical space, that was still centuries away. His system was really a search engine for truth, based on a given set of content.
Whereas Venn's system is a framework for variables that are devoid of content until you, the logician, assign them.
A very important nuance. Lull sets the stage for the mechanical dream, but the actual geometric spatial tradition developed independently, which brings us to a historical detour through the 17th century.
The confusing story of Christian Wise and Johann Christian Lange. They're often cited as a pre-Eulerian source for this.
The famous Wise-Lange controversy. This really came to the fore in the 19th century because Sir William Hamilton, who was a staunch critic of the rise of mathematical logic, he wanted to discredit Euler. He tried to claim the diagram method wasn't original.
And he pointed to who?
He specifically claimed that a German pedagogue, Christian Wise, had used these circles first in his 1691 work, Nucleus Logicae.
But John Venn, being the meticulous scholar that he was, he literally wrote the book on symbolic logic. He dug into this claim. And what did his investigation find?
Well, Venn, in his 1881 treatise, Symbolic Logic, established a crucial historical detail. The diagrams did appear, but only in the 1712 posthumous edition of Weiss's text.
So after he died?
Yes, and that edition had been heavily edited and expanded by his successor, a man named Johann Christian Lange. The original 1691 edition had no diagrams at all, so if anyone gets credit for that obscure 1712 appearance, it's Lange, not Weiss.
And even if we grant Lange diagrams 50 years before Euler, Venn still dismissed them. And that tells us something important about what makes a system historically significant, doesn't it?
It does. Venn rejected Lange's circles as an isolated evolutionary dead end.
A dead end? Why?
Because they lacked any systemic rigor. They were essentially just one-off, almost decorative illustrations used to visualize specific sentences, maybe a circle here, two separated circles there.
So it wasn't a consistent, systematic, standardized method. It wasn't a calculus for representing propositions or solving syllogisms.
Exactly. And without that standardization, they couldn't establish a continuous historical tradition. They were a footnote.
So if we bypass that Lange detour, the next true conceptual forefather we encounter is the towering figure of Gottfried Wilhelm Leibniz, co-inventor of calculus, and maybe the world's greatest advocate for formalized thought.
Leibniz, much like Lull, dedicated a huge part of his life to realizing the characteristica universalis, that universal logical language that could resolve all disputes through computation.
A kind of let us calculate philosophy.
Precisely. And he was constantly experimenting with visual logic to achieve this.
His most publicized attempts were linear diagrams, right? Using lines of different lengths to show the extension of concepts.
That's right. If concept A was contained within concept B, the line for A would be shorter and drawn inside the line for B. Simple enough.
But what's so historically frustrating and fascinating is that we now know Leibniz also worked privately with circular diagrams.
Yes, topologically identical to Euler's. In manuscripts like De Forma Logicae, around 1686, he sketched intersections and inclusions. He had the geometry down decades before it was made public.
So here is a man who invents calculus and independently conceives of the diagram, yet we don't call it the Leibniz diagram. Why did this conceptual genius miss the historical credit?
It's a classic case of brilliant ideas getting trapped in private archives. Those manuscripts were never published in his lifetime. They remain completely unknown to the wider philosophical and mathematical community through the entire 18th and 19th centuries.
And they only surfaced when?
During the comprehensive scholarly cataloging of his papers in the early 20th century, around 1903, an invention has to be public to establish priority. So the continuous historical tradition, the popularization, it flows directly and unambiguously through Leonhard Euler, which brings us to the moment the circle diagram truly entered the world of pedagogy and popular thought, the Eulerian paradigm.
Right. So we transition from this rarefied realm of, philosophical archives and combinatorial dream machines into the 18th century court. Leonhard Euler, the polymath who defined so much of modern mathematics, he introduced these ideas not in some complex academic paper, but in letters to a princess.
That's right. The context is vital here. Euler's logic diagrams appeared in his immensely popular work, Letters to a German Princess, on diverse subjects of physics and philosophy.
So these were actual letters.
Real correspondence written between 1760 and 1762, and then published in 1768. The recipient was Princess Friedrich Charlotte of Brandenburg-Schwedt. She was related to Frederick the Great's court, and Euler was basically her tutor.
So his goal was inherently pedagogical. He wanted to simplify and clearly explain the, as he put it, the drudgery of traditional dense scholastic logic for a curious but non-specialist student.
Exactly. And in letter 103, he introduces the circles. He writes that this method of drawing figures is very proper to facilitate our reflection on this subject.
So let's nail down the mechanics of the Euler diagram, because its intuitive nature is exactly what made it so popular. It relies solely on containment and disjointness.
It's a pure, simple spatial analogy. So you take the universal affirmative, all A is B. The visual syntax is completely literal. Circle A is drawn entirely inside circle B.
Containment means subset. Simple.
And if you want to assert no A is B, the universal negative.
You just draw the circles completely separate?
Completely separate or disjoint. The visual separation instantly communicates exclusion. This is incredibly efficient for simple syllogisms, which is why teachers adopted it immediately.
And for the particular affirmative, some A is B, you would draw the two circles overlapping, intersecting, to show that there's a shared, non-empty area where members of both A and B can live.
Right. Euler's system is a masterpiece of visual intuition for representing specific, known truths. However, this beautiful simplicity holds a critical, systemic limitation when you try to apply it to a generalized logical framework.
This is the fundamental flaw that Venn zeroed in on, the ambiguity of the unknown. Why does the Euler diagram become so problematic if we don't know the exact relationship between the classes?
Because Euler's system is designed only to illustrate actual relationships that you already know. It forces the logician to commit to a singular spatial depiction.
Okay, give me an example.
Let's take the proposition, sum A is B. Now, that statement is true if A intersects B, the classic overlapping circles.
Right.
But it is also true if A is entirely contained inside B.
Oh, because if all A is B, then it's also true that some A is B.
Exactly. And it's also true if B is entirely contained inside A. In all three cases, the statement sum A is B holds.
So if I draw the classic intersecting Euler diagram, the two overlapping circles, to represent sum A is B, I'm actually visually representing more than the proposition states.
You are. By drawing that classic intersection, you are creating a crescent of A that is outside B and a crescent of B that is outside A.
Visually, you're asserting that sum A is not B and sum B is not A.
Information that might not be contained in your original proposition at all. The diagram forces you to commit to a very specific kind of intersection, which is an unwarranted assertion if your goal is generalized logic.
That's a fascinating constraint. The drawing tool itself imposes an interpretation that exceeds the logical input. So if the underlying logic is uncertain or incomplete, the diagram can't really reflect that uncertainty gracefully.
It can't. The diagram forces the drawer to make an existential commitment to a specific spatial arrangement. This makes the Euler diagram excellent for illustration, but pretty poor for general algorithmic problem solving.
And I can only imagine this problem just explodes when you move beyond two sets.
It becomes an absolute mess. It creates a major complexity barrier. If you have three sets, A, B, and C, and you only know, say, that all A is B and no B is C, the Eulerian diagram has to be drawn ad hoc.
You have to invent it on the fly.
Every single time. You'd end up drawing circle A inside circle B and then circle C completely separate from B. There is no standardized template.
And because you only draw the necessary circles and exclusions, you don't automatically generate all the possible intersection regions. You don't get the 8 regions for 3 sets that Boolean algebra requires for comprehensive testing.
Correct. The logician had to constantly invent a new topological structure for every unique syllogism. And this lack of generality, this inability to handle ambiguity, it made the Euler method impossible to align with the revolutionary new algebraic logic of George Boole.
Which was about to just sweep the field in the mid-19th century.
The system needed a complete overhaul. It needed a standardized, comprehensive template.
And that need for a standardized template brings us squarely to John Venn. We're transitioning now from Euler's intuitive, illustrative method to Venn's rigorous algorithmic system.
Right. George Boole had already revolutionized logic by treating propositions algebraically, but the visualization needed to catch up.
And Venn, a dedicated lecturer and fellow at Caius College, Cambridge, he was acutely aware of the power of Boole's new algebraic framework.
He understood that for a diagrammatic method to be useful in this new era, it had to be 3 things: standardized, comprehensive, and compatible with the Boolean concept of the null set.
The idea that a logical class could exist in theory, but contain 0 members in reality.
That's the one. And he formalized his method in the landmark 1880 paper on the diagrammatic and mechanical representation of propositions and reasonings. His primary objective was to critique Euler's system for its lack of generality.
And this led to Venn's core innovation, which was brilliant precisely because it was a shift in focus.
A total shift. Venn stopped trying to illustrate propositions and started focusing on representing the classes first. He created what he called the primary diagram.
What defines the primary diagram? What makes it so fundamentally different from an Euler diagram?
The primary diagram is defined as a static framework that depicts all logically possible combinations of the sets involved before you apply any specific information. It's a comprehensive map of the entire logical space.
And the rule is simple and algorithmic. For n sets, you must generate 2 to the power of n distinct compartments.
Always. So if you're dealing with 3 variables, let's call them x, y, and z Venn mandates, that you always start by drawing 3 fully interlaced circles.
Which generates 8 distinct regions, 2 to the power of 3.
Exactly. You have to draw the center region where x, y, and z all overlap. The 3 regions where only 2 overlap. The 3 regions where only 1 set exists. And, crucially, the region outside all 3, representing things that are neither x, y, nor z.
By forcing the logician to start with this comprehensive canvas of all possibilities, the 2 to that n compartments, Venn completely removed the ad hoc nature of the Euler method.
It became a universal algorithmic framework, a template, just ready to receive logical input.
And once you have that canvas, you need a new syntax to encode the propositions, one that spoke the language of Boolean algebra.
A language that relies on the concept of the null set, or 0.
And that brings us to the famous visual syntax of Venn, shading. In a Venn diagram, shading has a very precise meaning that is often lost when we use it casually.
It's the key difference. Shading a region in a Venn diagram means that the class defined by that compartment is empty. It is null.
So if Euler separated circles to assert exclusion,
Venn drew the intersection and then shaded it to assert the certainty of absence.
let's take the universal negative. No A is B. In Euler, they're separate. In Venn,
They intersect, and you shade the region where A and B overlap.
Yeah.
You're algebraically stating the intersection of A and B is empty.
and this logic applies beautifully to the universal affirmative. All X is Y. In the Venn Boolean paradigm, this is treated as a statement of negation.
Right. It becomes the class of X that is not Y is empty. So you shade the part of the X circle that lies outside the Y circle.
This resolves Euler's problem of ambiguity instantly. An unshaded region in a Venn diagram carries no existential assertion. It just represents a logical possibility.
We don't know if members exist there or not. A shaded region, on the other hand, represents a logical certainty of absence.
The transformation is complete. The diagram stopped being a mere illustration and became a fully rigorous, functional, logical calculus.
And this commitment to mechanizing inference is really highlighted by Venn's parallel efforts in engineering.
Right, you mentioned the physical logic machine that Venn built. What did that look like? How did it show that his diagrams were blueprints for computation?
It was a fascinating device built around 1880. It used physical mechanisms, levers, and sliding planes to represent the compartments of the diagrams. Each of the 2 to the n compartments was physically there.
Okay.
When a user would input a logical premise by, say, manipulating keys or levers that corresponded to a proposition like all A is B, The machine would mechanically eliminate the regions asserted to be empty.
So if I asserted all A is B, the machine would physically cover up the region of A that's outside of B.
Exactly. And the final visible configuration of the machine represented the conclusion, the remaining unshaded, non-empty possibilities. Venn explicitly saw his diagrams as the topological map for the mechanization of inference,
Which is a direct conceptual precursor to the function of modern computing logic gates.
which operate by eliminating possibilities,
Yeah.
by setting compartments to zero. Now, if the shift from Euler to Venn seems like just a technical fix, the underlying driver was actually a profound philosophical pivot.
And that pivot is all about existential import. This single concept explains why the diagrams look so radically different even when they're representing the same idea.
Right, so let's define existential import. It's the question of whether a statement requires the actual existence of its subject to be logically valid.
Okay.
In the traditional Aristotelian logic that Euler was visually representing, the assumption was that universal propositions do imply the existence of their subjects. If you say, all horses are mammals,
Yeah.
you were assuming that horses exist.
And if A doesn't exist, the statement all A is B is considered either false or just a logical non-starter.
And as we discussed, the very act of drawing circle A inside circle B in an Euler diagram visually commits you to that existence. You can't draw an object with zero physical extension. The drawing itself asserts the subject exists.
But this is the critical distinction. Venn, following Boole, embraced the modern view, where universal propositions are purely conditional.
Exactly. The statement, all unicorns have horns, is logically sound. In fact, it's considered vacuously true, even if unicorns do not exist.
Wait, vacuously true. Let's take a moment to really drill into that concept because it's the core of Boolean thought.
Certainly. In modern logic, a universal statement like, all A is B, is logically equivalent to the statement, there are no A's that are not B's.
Okay. There are no A's that are not B's.
So if the subject A is an empty set, like unicorns, then that condition is never met. Since you cannot find a single unicorn that doesn't have a horn, the statement holds true by default. It is true by virtue of its subject being absent.
So it's not falsifiable. That is the null set concept in action. The null set is a valid and necessary part of this logical universe.
It is. And if Euler's visual system couldn't handle the null set elegantly, it couldn't handle the core of Boolean algebra.
So Venn diagrams were engineered specifically to accommodate this conditional nature and the null set. The diagram must not assert existence unless existence is explicitly started.
Precisely.
Let's walk through the visual comparison one more time, using the most common proposition. All A is B, so you can really see the philosophical difference reflected in the drawing.
Okay. In the Euler paradigm, to show all A is B, you draw circle A inside circle B. It's clear, it's illustrative, and it visually asserts the existence of A. The space A occupies is non-null.
But in the Venn paradigm, you draw A and B intersecting. Then you shade the crescent of A that is outside B.
Right, you're asserting that the class of A's which are not B's is empty. But the intersection region and the region of B outside A are left completely unmarked and unshaded.
And that unmarked region is the key. It represents the potential for existence, not the proof of it.
The diagram says if A exists, it must exist in this area, but I am not asserting that A exists right now.
And if I actually want to assert existence to give the proposition existential import, like some A is B, I have to take a separate action.
Yes. That's when you place a specific marker, usually an X, in the intersection region. The X is the visual symbol for existence.
So Venn requires two distinct steps or mark shading for universals, and X for particulars, to convey information that Euler tried to convey in a single, flawed drawing step.
And the genius of it is clear. Venn created a tool that separates the definition of the relationship, the shading, from the assertion of existence, the X.
And this ability to treat classes as hypotheses, empty or otherwise, made the Venn diagram indispensable for the development of modern set theory and all the binary logic that followed. We've established the critical logical leap of the Venn diagram, but now we have to address the physical limitations of those overlapping circles. While the three-circle Venn diagram is iconic, it's symmetrical, it's perfect, we quickly run into a geometric failure wall when we try to visualize more complex logic.
Indeed. For n sets, you need 2 to the n distinct compartments. So if we move to 4 sets, n4, we require 2 to the 4th, or 16 distinct regions.
And you can't do that with just 4 simple overlapping circles on a flat plane?
You can't. It's impossible to draw them so that every single possible intersection is present and distinct.
That seems counterintuitive. Why does simply adding a 4th circle not work topologically?
Well, when you try to overlap four circles simply, some regions get excluded. You might have a region where A, B, and C overlap, but it's physically impossible for the fourth circle, D, to intersect that specific ABC region without also excluding or simplifying some other region. The geometry of the circle is just too restrictive.
So Venn, having established the logical requirement of 16 regions, he had to solve the geometrical problem. What was his solution for N4?
Venn immediately recognized the limitation and proposed using non-circular shapes, specifically ellipses. He provided a precise construction for four sets using four congruous interlaced ellipses. And this construction successfully creates all 16 necessary compartments, with each one connected and distinct.
So that was the first true high-order Venn diagram. It shows he was committed to the algorithm over simple aesthetics.
He absolutely was. The visual standard for four sets isn't circles. It's a precise arrangement of ellipses that when you look at it, it looks a bit like a four-leaf clover where every leaf intersects every other leaf.
That's a good analogy. And it satisfies the 2 to the 4th requirement while maintaining some symmetry. But the problem continues to scale up. What about 5 sets?
Well, for n greater than 4, Venn proposed a general iterative construction. But it seems he sacrificed elegance for strict topological correctness.
What do they look like?
He ended up drawing these complex, interleaved curves that have been described as looking comb-like or like shoelace arrangements. While they were topologically sound, they generated the correct number of distinct regions. They were visually unwieldy, difficult to draw, and they lacked any rotational symmetry.
So they were impractical for anything other than a kind of academic illustration.
Exactly. Venn prioritized the logician's need for a comprehensive map over the visual simplicity that Euler valued.
Which means the quest for truly elegant, symmetrical, high-order diagrams became its own specialized field of mathematical research in the 20th century.
A fascinating little offshoot of logic, yes. And one of the most famous figures here is A.W.F. Edwards, a British statistician and geneticist. He's responsible for the system often called the Edwards-Venn diagram.
That's the one that uses the cogwheel pattern, right?
Yeah.
How does he manage to maintain symmetry for, say, 5, 6, or 7 sets?
It's very clever.
Yeah.
Edwards solved the problem by abandoning the flat plane at first. He projected the logical space onto the surface of a sphere, where it's easier to arrange symmetrical dividing lines.
Okay.
When you project that spherical arrangement back onto a flat surface, you get this visually distinctive, rotationally symmetric cogwheel pattern. And this method can generate symmetrical diagrams for pretty much any number of sets.
And there's a stunning physical manifestation of this.
There is. To honor Venn, Edwards designed a famous stained glass window in the hall of Caius College in Cambridge. That window depicts the complex but beautiful 7-set diagram.
Showcasing the 2 to the 7th power.
Or 128 distinct regions in a perfectly symmetrical layout. It's an incredible testament to the marriage of mathematics and artistry.
Imagine trying to analyze 7 variables in one visual image, where every possible permutation of those variables has its own little compartment.
And we also have to mention the work of Branko Grunbaum, who explored the geometric properties even further. He showed that a radially symmetric arrangement is possible for N5 using 5 congruent ellipses, which results in a complex yet symmetric 5-pointed star pattern.
And this leads to a fascinating theorem about symmetry and prime numbers.
It does. Related to Grunbaum's explorations, there's a finding, often summarized in relation to Henderson's theorem, which suggests that Venn diagrams that are both simple, meaning only 2 curves intersect at any one point, and rotationally symmetric.
Exist if and only if the number of sets, n, is a prime number.
Exactly, which confirms that the seemingly simple act of drawing overlapping circles for logic involves some deep, unsolved, and really counterintuitive geometric principles.
We have meticulously traced the evolution of the diagram from Lull's combinatorial aspirations through Euler's pedagogical clarity to Venn's algebraic rigor. But now we encounter the final and most ironic twist in the entire story, the naming itself.
The irony is profound. John Venn, the man who performed the necessary algebraic overhaul, consistently refused to name the creation after himself. In his 1880 paper and his comprehensive 1881 book, Symbolic Logic, he explicitly referred to his creation as Eulerian circles.
So he saw himself as a reformer, not an inventor of a whole new class of diagram.
That's right. He viewed his work as the necessary completion of Euler's scheme, making the visual vocabulary that Euler established functional for the demands of Boolean algebra.
He actually wrote, of these schemes, one only, viz. That commonly called Eulerian circles, has met with any general acceptance.
He fully acknowledged Euler's priority in making the circle scheme famous.
So if the inventor himself insisted on calling them Eulerian circles, who then is the specific academic figure who actually coined and popularized the term Venn diagram?
That credit belongs to an American philosopher, Clarence Irving Lewis. He lived from 1883 to 1964, and the term made its debut in his landmark 1918 book, A Survey of Symbolic Logic.
100 years after Euler and almost 4 decades after Venn's paper. Why did Lewis feel the need to introduce a new term when Venn himself was content with the old one?
Well, Lewis was writing a historical and conceptual review of the entire field of symbolic logic. He desperately needed clean, unambiguous terminology. By 1918, the distinction between Euler's simple illustrations of specific truths and Venn's comprehensive map of Boolean possibility was just too crucial to ignore.
So the term Venn diagram was created specifically to codify that logical distinction. Lewis recognized that Venn's introduction of the primary diagram and the shading syntax was a fundamental, separate logical invention.
One that deserved its own name to distinguish it from the limited, Aristotelian method of Euler.
And Lewis's nomenclature achieved two things. It correctly credited Venn with the foundational logical rigor, and it allowed academics to stop debating which kind of circle diagram they were talking about.
And the name stuck, cementing Venn's place in history.
And this codified distinction allowed the diagram to just explode into modern pedagogy and technology. The most recognizable impact for our generation was probably the new math movement of the 1960s.
Oh, that educational reform was crucial for public awareness. The movement shifted elementary math instruction from just rote calculation to emphasizing the conceptual foundations of mathematics, especially set theory.
And the Venn diagram was the perfect visual tool for this pedagogy. It was intuitive, it was rigorous enough for basic set operations like union and intersection, and it was highly visual.
Millions of students, therefore, learned set theory through those overlapping circles, even if the philosophical nuance between the empty set in Venn versus the assumed existence in Euler was, often lost in the elementary school curriculum.
But the deepest, most foundational impact is found in engineering and computer science, where the binary nature of Venn's system is indispensable.
Inside or outside, 1 or 0.
Exactly. Venn's framework, with its compartments representing every possible logical state, translates perfectly to digital logic. Every single digital circuit is based on Boolean logic, gates, AND, or not fate, which are fundamentally operations on sets defined by the Venn diagram.
And this isn't just theoretical either. You can see the direct topological link in tools used by electrical engineers every day.
Like the Carnot map.
Exactly. A Carnot map is a common visualization tool used by engineers to simplify Boolean algebra expressions, especially when they're designing circuits. Topologically, a Carnot map is just a rectangular, stretched-out Venn diagram.
Where the shading of regions corresponds directly to zero states that need to be eliminated from a circuit design.
Right. So what started as a Majorcan mystic's dream of mechanical truth, refined by a Swiss polymath, and systematized by a Victorian logician, truly became the fundamental blueprint for the hardware we all rely on today. It provides the very grammar for information processing.
And today, these diagrams are used everywhere data is analyzed. In genomics, they illustrate shared genes between species. In linguistics, they map overlapping features of languages.
And in business analytics, they often appear as area proportional diagrams, which kind of marry the geometric intuition of Euler, where the circle size means quantity, with the topological correctness of Venn, where the regions are comprehensive.
It's a true palimpsest, one idea layered on top of the other. So let's bring this all back together for you. The Venn diagram is not a singular invention, but a chronological layering of logical ideas.
We can summarize the cumulative contributions. Ramon Lull gave us the original combinatorial dream, the revolutionary idea that complex logic could be externalized and mechanized.
Leonhard Euler provided the geometry and the popular visual vocabulary, the circle diagram making logic intuitive, simple, and accessible for the first time.
John Venn provided the crucial algebraic system and the logical rigor, the primary diagram and the shading syntax. He transformed a simple drawing into a generalized calculator fully compatible with modern Boolean logic.
And finally, Clarence Irving Lewis gave us the name, codifying the necessary distinction that allowed Venn's method to achieve academic clarity and widespread adoption.
So the next time you look at those 3 overlapping circles, remember the philosophical argument that's embedded within them. The Euler diagram shows us what is true in a specific instance. It asserts existence as it illustrates a reality.
But the Venn diagram, through its comprehensive framework, its algorithmic guarantee of the Teutothon regions and those deliberately unmarked, unshaded spaces, it allows us to map the entire universe of what might be logically possible, regardless of whether it exists or not.
You're looking at the foundational logic of modern computation, a visual map of conceptual potential that includes not only what is, but the necessary absence of what is not.
That distinction between what is and what could be is a powerful thought to carry with you. Thank you for taking this deep dive with us.